Hello, and thank you for coming back for the discussion of the Managerial RQ policy. In this video, I have two objectives. Number one, to show you how we can find the inventory parameters, that is, the order quantity and the order point R, if a managerial policy is in place. And to do that, we're going to be taking a look at this worksheet right here. Notice, as always, we have certain cost, demand, and lead time information. That's what you see right up here, and importantly, the one piece of the puzzle that is missing is the back order cost per unit. And because we do not know what will cause us to stock out, we cannot possibly estimate back order costs. In other words, we cannot really set up a total cost function that would include all relevant costs. And because I cannot set up a total cost function, I cannot optimize it either. And that has a result that I cannot define the truly cost minimizing, or in other words, optimal values for the order quantity Q and the reorder point R. And if that's the case, then remember we fall back to what we call the managerial policy. That is, we use the basic EOQ as the best estimate of an at least close to optimal order quantity, and we'll have to rely on managerial input as far as the service level target goes. In this case, it would be 90%. So as always, what we're going to do is we're going to complete this worksheet from top to bottom. And once we're done with that, I want to spend just a little more time talking about the N of R, how this expected stock out quantity per cycle is actually calculated. So that'll be the second objective of the video. So let's jump right in and let's take a look at the order quantity Q. It is the square root of 2 times annual demand times the order placement cost K divided by the holding cost per unit per year, H. In this case, 240 units. And then I simply move on down. Notice that all my demand and lead time information is given in years, so no conversion is necessary, such that I can calculate mean demand during the lead time as lambda times mu sub tau, which is 292 units, and sigma, the standard deviation of demand during the lead time, would be the square root of mu sub tau times the variation of demand, which is mu squared plus the average demand squared, times the variance of lead times, which is sigma sub tau squared. So here we get a value of sigma of 217. And again, notice we have this managerial determined service level target of 90%, which I can then translate to a value of z and a standard norm invariant using the norm's inverse function. So I get a value of z of 1.28, and I can use that to define my safety stock requirement, which of course is simply z times sigma, in this case 278 units. And then my reorder point, of course, will be equal to mean lead time demand, plus the safety stock, which we just calculated, and that will give me a value of 570 units. So again, these two values that you see highlighted in bold, Q, which is 240, and R, which is 570, those define the managerial RQ policy we are looking for here. So then what I can do, and again, this is of course goes beyond just defining the RQ policy, I can figure out what would be the resulting fill rate, and to do that I need to calculate the N of R, the expected number of units out of stock per cycle. Now the good news is I can simply do this by implementing the formula that was shown here. So let me go right ahead and do that. And you see I will get a value of 10.25. And this means that given these values of Q and R, I would on average expect to stock out 10.25 units per order cycle. Now that I have this value, I can also calculate the fill rate, which of course is 1 minus N of R over Q. So you see, I would get a fill rate of about 96%. And now it's up to the manager, of course, whether that's actually an acceptable value or not. So let me go back a little bit to this value of N of R. Now remember, it is called N of R because the number of units that I expect to stock out by per cycle is a function of how I define the order point or R. In other words, if I were to increase my reorder point, I would of course expect to see a decrease in N of R. So let's see if that's true. Let me change alpha from 90 to 95%. And of course, what we're going to see as a result is that the safety stock increases, the reorder point increases, and ultimately the stock out quantity would then decrease. Remember, down from 1025 to 4.53. And as a result, then the fill rate increases. So naturally, the number of units I can expect to stock out by will be a function of the reorder point. That's why we call it the N of R. I just want to use these graphs down here to illustrate to you what exactly this N of R calculation does. And when we look at it visually, I think you'll see that it's not actually all that complicated. So what we see at the top here, the top two graphs are what we call probability density functions. They are also called probability distribution functions. We have two versions, and they are really the exact thing. The only difference is being that one to the right is a standardized probability density function with a mean of 0 and a standard deviation of 1, and the distribution to the left is a non-standardized distribution that has a mean of mu and a standard deviation of sigma. Notice just the slight difference in notation. What we call f of r in a non-standardized probability distribution function would be called f of z in a standardized distribution function. And that's because in the non-standardized distribution function, we have this reorder point r right here that in a standardized function would be called z. And you all probably remember learning about or seeing z-tables. And these tables are standardized. In other words, they apply to any distribution. Those are simply defined for a specific standardized distribution with a mean of 0 and a standard deviation of 1. But we can then use the value of z to calculate the reorder point r, which is exactly what we just did. So this is just to briefly illustrate the difference between standardized and non-standardized distributions. And likewise, we have a different way of depicting these probability density functions, and that's when we talk about cumulative density functions. Again, all these graphs do is they depict the same thing you see on top, but in a different manner, specifically in a cumulative manner, which is why we see this sort of S-shaped curve. And again, notice the difference between a non-standardized cumulative density function and a standardized cumulative density function. Again, the same idea. In the standardized function, I have a mean of 0 and a standard deviation of 1. And what I'm really interested in here is determining the N of R, the stockout quantity per order cycle. And that is really the area to the right of the order point R and to the north, if you will, of the cumulative density function. This is the area right here that I'm calculating when I calculate N of R. And the standardized value of N of R is what would be called L of Z. So just when you read textbooks and you come across these differences in notation, that's really where it stems from, the difference between talking about a standardized versus a non-standardized function. So the important thing here simply is if I have a given value of alpha, and recall that alpha will be the probability mass under the normal distribution to the left of reorder point R. I can convert that mathematically through a couple of steps into an expected stockout quantity per cycle, and effectively what I do is I translate the PDF, the probability density function, to a CDF, cumulative density function. And you see here, what is the probability mass 1 minus alpha in the probability density function right up here becomes this little segment to the north of the cumulative density function all the way up to the bound of 1. That is 1 minus alpha. And then the area to the right of that, to the north of the curve, that is really what we calculate when we calculate N of R, the expected stockout quantity per cycle. One last thing I want to briefly illustrate here, and we've probably discussed this in a previous video, but it is a nice way to sort of double check whether your calculations actually make sense and what to look at, and that is to look at imputed backorder costs. So remember, I do not have backorder cost information here. So what I do instead is I rely on some managerial input to give me a serviceable target, either a type 1 or a type 2 serviceable target. Now what I can do though is I can work backwards and then infer what the implicitly assumed backorder cost would be. The reason I can do this, remember, is when I calculate an optimal in-stock probability alpha, I calculate that as 1 minus Q times H over P times lambda. In other words, the optimal in-stock probability is a function of the magnitude of backorder cost P. Now what I can do is I can rearrange the formula to tell me what the value of P is. That would be implicitly associated with a given value of alpha. So all I do is I calculate the imputed backorder cost P as Q times H divided by, in parentheses, lambda times 1 minus alpha. And now make sure you use proper parentheses here. So you see for a value of alpha of 95%, I would get an imputed backorder cost of $12.50. Notice that the unit order cost is $19 per year, so it is fairly safe to assume that the unit value is around $100, give or take. So fairly substantial, so backorder cost of $12.50 might actually make sense. Now, if of course I increase the value of alpha, we know what will happen to the imputed backorder cost. It will increase as well. So let me change alpha to 99%, for example, and now you see, of course, I won't stock out much at all because I have so much safety stock. And now the imputed backorder cost is much, much greater. It is almost $62.50. And now the question becomes, is this still realistic? Or conversely, if I set an alpha target of, let's go back to the initial 90% value, then I get a backorder cost of just about $6.25. Again, I cannot tell you whether or not this is the right value, but at least it gives me a checkpoint to see whether my assumptions here, whether my managerial defined service of the targets actually makes sense. So this concludes my discussion of the Managerial RQ policy. If you have any questions, as always, please remember, ask me and I'll be happy to help you.